the Robot Learning and Reasoning Lab, where he advances robotics by combining machine learning, computer vision, and planning in order to build adaptable general-purpose robots. He also is a researcher at NVIDIA AI and earned his PhD in computer science from Stanford University with Feifei Li and Silvius Savarese. And Danfei's work has earned significant recognition, including a National Science Foundation Career Award, and his research portfolio includes award-winning publications and innovations in imitation learning, long-horizon task reasoning, and robot learning systems. And with that, we're very excited to hear about your work, Danfei. Take it up.
All right. Thanks, Oier, for the introduction. Hi, everyone. Cool. All right. So I think the lecture today is about imitation learning, right? I was looking through the syllabus. Is that right? Oier?
What's that?
Could you confirm? Is the was the lecture today about imitation learning?
Imitation learning,
okay.
Yes.
Awesome. All right. So that's a fitting topic. So, okay. So, but it's a more kind of I wouldn't say contrarian view, but more kind of alternative view for imitation learning. So hopefully that connects to what you've seen today. Specifically, the talk I'm going to give today is really examining a very simple hypothesis that we can scale robot capability with human experience data. And most robot learning today kind of still depends mostly on teleoperated demonstration data. And in contrast, VLMs are successful because they can learn from naturally occurring human data from internet. So the question is, can we scale can robot learning scale the same way from natural human behaviors? So to think about this, let me start with a more conceptual view of robot learning. So my view is that modern robot learning has three core couple components: data source, the learning algorithms and models, and the physical system. You cannot change one in isolation. Progress really comes from co-designing all three of them all together. So I call this the triangle of robot learning. And from this perspective, we can now kind of check a recent trend shift in the field, which is a growing focus on changing the data source rather than only improving the models. The most dominant trend today is perhaps learning from teleoperated demonstrations, and we can at the same time examine their algorithms and hardware systems. So just by manually, so for those of you who are have not done this kind of research before, just kind of giving some examples where just by manually control the robot with some devices like VR controllers, you can collect expert demonstration to train robot policies end-to-end from pixel abstractions. And we've seen this both success in academia and industry, a lot of really impressive demos for solving tasks we thought were previously not possible, such as doing laundry and making pizzas. So Oier should have already covered this kind of topic today, but to give you just more practical sense of how we actually collect teleoperation data and train policy model. And just to give an example was a work I did back in 2020. So when a human operated a robot using control device, such as like a smartphone here, we capture two streams of data, what a robot senses and how it should act. This gives you really the ground truth control signals for a given observation input. And the important point here is that we're not just kind of transferring the abstract knowledge by perceiving and acting through the robot's body. We're training a model, a policy model, by kind of transferring this kind of embodied sensor motor knowledge that is not really existing in today's internet data. So that's really kind of not really naturally occurring human knowledge, but more of kind of deliberate demonstrated data. And when we revisit a triangle, teleoperation creates really a tight coupling, a model of these three components. Data is generated only when humans act through a specific robot, and algorithm then learn from the robot's specific data, and the resulting policies only work on the same hardware configuration that you collect data on. And this really prevents the system from scale. To collect more data, you need more robots, and to change the embodiments, you really need to recollect data on that target embodiment. So this leads to a really tight bottleneck, or a very tight knowledge transfer bottleneck. Humans have enormous sensory motor knowledge about the physical world, but we only capture the knowledge when we deliberately act through the robots, and this knowledge is really like kind of waste of human knowledge, right? We're kind of throw away most of our natural knowledge about how we interact with the world. So the question is, can we transfer the sensory motor knowledge from humans to robots at scale, similar to how it's happening in vision and natural language processing? And our proposal is to break this bottleneck by removing the data from the data collection loop. So instead of recording humans acting through robots, we learn from humans act naturally in the world. This kind of data contains rich sensory experience, can be collected at a much larger scale with our robots, and it really doesn't require any intentional demonstrations. So the question then becomes whether we can turn this human experience into useful supervisions for robot policies. So as I mentioned before, we cannot change one thing with robot experience as a data source. We have to rethink how to capture and learn from the data, as well as the rest of the robot hardware systems. And this brings us to our first research milestone, which I'm not sure some of you have seen it. It's called Egomimic, Scaling Imitation Learning via Egocentric Video. The core of this project is to capture embodied human data with an egocentric view with wearable devices, which means that we can collect this data anywhere. Unlike third-person views, egocentric data really capture how we humans perceive the world at an eye level. And specifically, we use the Project RA glasses, which is kind of a pair of smart glasses to capture this data. Kind of gives you the essential sensory experience that I'm going to talk about a bit later. And our work really is about turning these raw data stream into embodied human data that can be treated as equals with robot data. So we no longer treat kind of human data as human data, but more of human as kind of different kind of robot. We have input and output. We're just trying to capture it and put it alongside the robot data to train them on. And in order to do this, we have to bridge sensing, action, and kinematic gaps and develop really this joint policy and learning architecture that scales primarily with human data. So let's first talk about how to align embodiments and viewpoints between human robots. So for embodiments, it's not really like a challenge as of 2026, but back then when we started this project in 2023, there weren't many kind of robots, human-like robots that kind of mimics the embodiments of humans. So we actually had to kind of think about how to design lightweight and lean robots that are human-like. So we kind of built our own robots with 2 6-op arms and some of these devices. But one interesting thing is that we actually mimic the viewpoint of humans, and we actually even use the exact same sensing device as humans, which is this pair of IR glasses. So we mount IR glasses on a robot so that have the very similar camera hardware specification and viewpoint so that we can minimize the inter-embodiment gaps. Among the many problems we had to solve to learn from egocentric data, I want to kind of highlight one very interesting one, which is the viewpoint shifts. When we work with robot like ours, the robot's grip moves relative to like a fixed reference frame, right? You can easily get actions trajectories in the fixed kind of reference base frame. But with egocentric human data, like the ones I just showed you on the left, the chef cooking, preparing dinner, we kind of, our head naturally moves, we look around, check workspaces, focus on different tasks. This means that the hand position tracked relative to a moving reference frame. And we need to really stabilize this reference frame to make human hand motion like usable as supervision, action supervision for robot learning. And luckily, we were able to do this because Arya already gave us like a really good SLAM system that can sort of track the head motion relative to hand or hand relative to head so it could actually turn us into a stable reference frame. So in the first row, we have these kind of moving referencing where head is everywhere, hand is everywhere. But now we can actually transfuse this fixed work coordinate frame from SLAM map to transform all the trajectories to a fixed base frame. So this allows us to create these kind of very stable trajectory relative to a camera frame. So with all of this kind of input and output aligned, we actually were able to design a very, very simple kind of behavior cloning system. You probably have already seen this in today's lecture. So it's really a supervised learning problem with you have input, observations, let's say sensing, perception, and output actions. And we basically put both human robot data together, did some normalization that if you're interested in, you should read the paper. This is really kind of how we put together the system. And our hypothesis is that if you just train this policy with more human data, the robot performance would increase with just that same amount of robot data. So the hypothesis is that we want to drive the robot performance primarily with human data. And we test this kind of policy on a variety of different tasks, like bag and grocery tasks, where like kind of you have to lift up back handle and put all of these kind of groceries in a bag. You can see that it kind of is a closed loop policy that kind of corrects the mistakes, and folding clothes, and also making pour-over coffees for our graduate students. I'll just let this video finish playing. Yeah. It's a very hard task, sees once in a while. But the true question is that does Egomimic scale with human data? And to check this, we actually did this kind of tiny scaling law experiments where x-axis is hour of data you collect either on human robots, and y-axis is the score of performance. And you can see that with only robot data, this blue line, you can see this kind of mild scaling curve with more teleoperated robot data, the performance gets better. But if at sort of once you have a certain amount of robot data, if you just add this human data into the training mix, you can dramatically see this dramatic jump in the robot performance. And this basically validates our hypothesis that human data is a viable way to drive up the robot performance. And one of the reasons is that we humans actually kind of demonstrate a lot faster than teleoperation. For some tasks up to 10 times faster than teleoperation. And remember that also the nice thing is that we don't need a robot in the loop, so we can just provide this demonstration anywhere. So we also moved this robot to kind of variety part of the campus to show the robustness of this. These videos are on the website, so if you're interested, you can watch them. So in the interest of time, I'm gonna kind of skip and talk about sort of like what kind of robot learning triangle we had built, which is that we now have this human data source as the embodiment, as the data source, human experience as data source, and we had to change our physical robot embodiment, also algorithms. But as you can imagine, that just co-training human robot data is not the most sophisticated algorithm out there. It's essentially still just behavior cloning. So the question is, can we do better? And before that, we have to check what's missing, right? So what we've seen in Egomimic is scales. So it scales with the robot policy performance with human data. What is missing really is that those tasks that human administrator has to exist in the robot data. So to say, we have to collect these kind of paired distribution data from human robots in order for the robots to kind of improve its performance. And the dream of our kind of vision really is that we want to have this kind of zero-shot transfer, which is that we want the robots to be able to do something that only exists in human data. So, and clearly this co-training objective, like algorithms, still cannot achieve that. So what's missing? Essentially what we are hypothesizing, which is like ideal picture of like how robot can do the zero-shot transfer, is to learn this kind of generalizable domain invariant latent space, such that let's say you have human data of folding shirts and robot data of folding shirts, which are blue and orange dots, and you map them into this latent space, and your policy model basically decodes this into an action. And when a new batch of data arrives, folding shorts, which doesn't exist in robot data, but only in human data, your encoder, this domain invariant latent space, should ideally map this to the same space so that the policy can still generate reasonable actions for this new task, while you don't really have any robot data for. So that's our ideal picture. But what happens in practice, as discovered by our student lead, Ryan, is that it's actually not learning this invariant space. They are like pretty separated. Human robot data are kind of, they're very isolated. They're really just two clusters. So the question, well, there are many reasons, other ways that we can kind of enable this zero-shot transfer, but our specific hypothesis here really is that maybe if we can pull these distributions together to form this latent space through some learning algorithms, we could actually enable stronger human-robot transfer. And this is where sort of our policy, our newest paper called Egobridge come in. Without getting too much details, this is really kind of a joint distribution alignment algorithm between human robot data. So we'll joint aligns the state action or opposition action distribution between the two data sources via optimum transport. So in case you have not learned, so optimum transport is sort of this like distribution matching algorithm, and if you implement this in a specific way, it's differentiable, so you can actually use this as a way to kind of pull distributions together without destroying their respective marginal distribution structure. So kind of just gonna skip over the equations here, but the takeaway here is that it's a very general algorithm. You can use a variety of ways to decide on how to pull these distributions together, and by designing this cost function. So the cost function we use is kind of matching their action shapes. So human robots should have roughly similar shape of, like, so to say, shape of trajectories when they do similar things. We use that as a supervision to draw them together, but you can use other things like language descriptions or other reliable weak supervision signals to pull these distributions together. And the algorithm itself is quite simple, so it's just an addition of auxiliary loss on top of our Egomimic pipeline, so it's kind of plug and play. So there, instead of one loss, you have two losses. And as a result, we do see that on the left side, Egobridge largely improved the alignment between human robots, because it's actually a bit hard to see, but you can see all of these orange dots behind all these orange dots. They're actually blue dots behind them, so they're kind of more or less aligned. And yeah, so there are parts of the data that do not align, but we observed that empirically the model does improve performance. And if you actually visualize the nearest neighbor points between human robot, they actually show that very similar behaviors. If you visualize the images a bit. So we do see improvements in performance, and also we also see some early signs of solving tasks that are only seen in robot data, for example, in human data. For example, we designed this task where the robot has to basically, so you start from the beginning. So human demonstrated on this, all of these regions where you kind of open the drawer and put something in it. And robot data only covers the purple kind of quadrants of these. So there's only one region that's not covered by robot data, but only by human data. So we can see that robot is actually able to solve this task with a significant boost in performance. So most of the methods will not be able to do this kind of knowledge. So kind of just to kind of tie it back to triangle. So we were able to kind of improve the algorithm to make sure that the whole cycle kind of are consistent with what we are trying to achieve here, which is learning from human data. But now what we've been doing is kind of largely just focusing on tabletop manipulation data tasks. So what if we want to change this for something like a humanoid, right? Like where it can actually move around and do things in a room scale. So we have to kind of adapt our algorithms and whole systems to accommodate that. So it's actually a very interesting topic because teleoperated mobile manipulation has been there for a few years. I'm not sure if you guys seen this demo from this paper called Mobile Aloha, where they kind of tell up a robot to do a variety of things and train a behavior cloning policy on top of that, which is actually quite impressive. But at the same time, mobile demonstration are really, really hard to collect because you actually have to move the robots around, and it's also not very intuitive to do mobile teleoperated demonstrations. But human data, on the other hand, does contain all of the information we need to actually to kind of learn to behave in a mobile way. And specifically, if you look at the prior ARIA glasses, we could actually extract a lot of information from just one task demonstration. For example, we can have the hands, actions, full slam map, and where the person is sort of in any given time. So we can reasonably expect it to recover some sort of mobile manipulation policy from this data. Right? So with that in mind, our student developed an algorithm called Emma, which is very similar to Egomimic, but it's just co-trained from human robot data. And we actually had to do a lot of full stack design in terms of both the robots and algorithms so that we can mitigate the difference between the bigger gaps between human robots when you start doing mobile manipulation. So I won't go into too much details of these algorithms. If you're interested, you can search up the paper. But at the end of the day, we're able to train a policy that does these kind of mobile manipulation tasks through end-to-end learning. And we were also able to do these kind of long-run tasks like grocery shopping, not just like bagging groceries, was just a end-to-end learning pipeline. You can see that everything is driven by egocentric view, basically. Yeah. And we were able to see a kind of a drastic kind of boost in performance compared to just teleoperation data. So given the same amount of time, if you combine like fixed base manipulation teleoperation policy plus mobile human data, it vastly overperforms the mobile teleoperated demonstration data. And we see a very, very clean scaling curve as you add more human data into the system, the policy performance increases. And after that, we started working on a few other things around this. And one of the most recent kind of ongoing work is to really deploy similar things to a full-blown humanoids with dexterous hands and everything. So this is really our early kind of experiments on testing the replay of from human data to robots. Yeah. Okay, so I want to kind of end this talk. How much time do I have?
You still have time. All good.
I can't hear you. Sorry.
You still have time. Okay,
good. All right, awesome. So, yeah, I kind of want to reflect on what we built. Like, there are many other works that happen in our lab that build around kind of this triangle, like better hardware, better algorithms, better human experience. So we, in this talk, we talk about Egomimic, which kind of first time that established this triangle for human data. We improved the algorithm, and we improve the sort of the hardware, and we also improve the whole stack system. But there are many other open questions out there in order to better leverage human data for robot learning. I would kind of summarize these into three categories. One is hardware systems, the other is data algorithms, and third is the whole research community. Specifically, we're interested in how to better capture human experience context, how to design better hardwares for robots so that they're more human-like, what roles should human and robot each play in a learning algorithm, and how to drive the collective progress for learning from human data for robot learning. So the claim here is that we've already kind of captured certain aspects of human data, human experience through these kind of wearable devices. But if you think more about this, first-person videos are not sensory motor experience, and they are not decision-making context. So there are a few kind of layers of gap between first-person video all the way to things that are kind of decision complete, so to say, for robot learning. First of all, our sensory motor experience is multimodal. It's not just first-person video, right? So we capture the videos effectively, but on the tactile side, for example, we're nowhere near capturing the complete force and tactile signals that we use daily to kind of do this kind of fine-grained context-rich manipulation yet. And on the other side, and the context necessary for decision-making is also more than just instantaneous observation, right? It's not just mapping my current observation to an action. If you look at this first-person video again, the reason that the chef turned to the other counter to get the ingredient or to adjust the heat occasionally is not to only based on this instantaneous observation, but rather what he remembered from a few minutes ago that he had prepared this ingredients, and he had years of training on how to cook certain ingredients. We're still far from assimilating this kind of knowledge to our robots through end-to-end learning. And we're not just care about like kind of robot kinematics. Can we kind of make so the other side of things is that can we make robot hardware and systems more human-like? For example, we designed this kind of very simple robots to show that if you have agile, lean robots, you can learn from human more effectively. But what if you make robots even more human? And in our recent work from NVIDIA, we actually built this kind of a even more human-like upper body with 22 degree of hands and better arms. We're able to do these kind of tasks that we were not able to do with the systems we had before. So the question then is that if we make robots more human-like, can we actually learn more effectively from human data? And on the second, on the data algorithm side, kind of what we claim is that human embodiment is universal and has scalable data source. More human-like robots will make human data more useful for robot learning. So if you kind of think about this in your head, what we're claiming really is that we have a lot of human data and we have some embodiment-specific data to ground this prior knowledge. So the question is, what roles should human and robot data each play in this whole setting? Most of you, some of you probably have seen kind of this analogy of like our data being kind of a pyramid where you have more scalable data sources on the basement, on the foundation, also more scarce or more kind of high quality data on the top. So for the human robot data, our pyramid will look like this. But where we kind of fine-tune or co-train human data with robot data. But I argue that's just like how we can actually flip this pyramid and say maybe more robot data or high quality robot data or better policy can actually enable us to better learn from this human data. So we may be able to kind of flip this pyramid and say it's only if we have more kind of better robot foundation model can we better learn from human data. So recent collaboration with Pi Physical Intelligence will kind of validate this hypothesis by saying that maybe stronger foundation policy model can enable better human-robot transfer. We saw that indeed, if you actually pre-train your robot foundation model better, like with more cross-embodying robot data, we actually can see a bigger jump when you fine-tune it with human data. So, and we also saw this sort of in this kind of Disney embedding map, where with better VLA model foundation models, when you add in human data, they actually align better with the in distribution robot data. So if you recall the Egobridge picture. Now we're saying that if you have better VLAs, you achieve a similar effect of human-robot alignment. And finally, the question is, can we drive collective progress? So I reckon that learning from human data is still kind of I wouldn't say a niche field, but it's actually a resource-intensive field. We've seen a lot of kind of collective efforts on collecting a lot of robot data together. For example, Oier, I think, was also part of some of these efforts. The question then becomes, can we actually kind of drive this progress of the whole research community by building some shared infrastructure from, let's say, data sets to policy learning algorithm to evaluation pipelines to close the whole loop. And the hope is that if we kind of open source all these data sets and infrastructure, we are able to better drive the performance, drive the kind of collective progress of the community. And I kind of just give you a very sneak peek of what we're going to release in a few weeks. It's called Egoverse. It's exactly that. So we're able to kind of put together resources from many different institutes and also companies to build this data sets and all the infrastructures to deploy these human-to-robot transfer algorithms on a variety of different embodiments. So this is roughly what a data set looks like, roughly 1,300 hours of human data. but it's still increasing. So every day we have companies kind of contribute their data, some part of their data into our repository among our academic partners. And we also have these kind of interfaces to browse through these data on the web portal. And we also, across 3 different universities, we cross-validate this data be useful for robot learning. So, for example, we were able to show like the exact same policy learning pipeline deploy on 3 completely different robots and achieve similar performance jump by learning from human data. Okay, I think I'm slightly over time. So here are the 3 main papers discussed during this talk, and here are the funding indices. And if you're interested in learning more about the type of work we do, you're welcome to visit our lab website or just email me if any questions. And thank you.
Cool. Thanks a lot for an amazing talk. Does anybody have any questions for Danfei?
Thank you very much. Hello, thank you for a nice presentation. I have a question about the quality of the data that you can get by human egocentric. You've talked in the beginning of the class.
It's a bit muffled. Can you maybe hold your mic closer to you, or it's a bit hard to hear?
Can you hear me better now?
Yeah, better, yeah.
Okay, so the question I have is about...
Yeah, sorry, go ahead.
It's about the quality of the data that you can get using egocentric human data. Because when you teleoperate, you get like high quality data, I imagine. And like when you operate using humans, you don't get the exact same type. And I wanted to know what the bridge is and like how you're able to improve teleoperation data through humans. Yeah,
I think that's a very it's a very fundamental question. Is that what do we learn from human data? So I have a very very long answer to this question, but let me just summarize my thoughts. Is that right now today, how we're using these human data is really just kind of adding that into a training mix, and just use our intuition to bridge as many kind of gaps that we see as possible. For example, humans move a lot faster than robot teleoperation, so we need to kind of align their speed together so that we can learn share representation. We move our head a lot, so maybe we will tell our demonstrator not move our head a lot so that I have a stable view. But so that we're kind of treating this as a distribution alignment problem so that we can make humans more robot data-like. But in the future, I think this should be the other way around. We should actually make our robot be able to generate more human-like behaviors such that it can better leverage human data. So I don't think that directly answers your question, but at least that's kind of for the time being, where we have hacks. In the long-term future, I think the future is bright in the sense that once we have better hardware, we can more systematically solve this problem.
Cool, thanks. We have one more question here.
Hi. How do you estimate forces from the video?
We don't. Right now, we don't. We actually there's one paper that I did not talk about called Mimic Touch that we start to use tactile, not force. Very importantly, not force, but with fingers. Sorry.
Okay. Is that the problem? It must be scary to deploy robots without knowing forces.
Yeah, force is hard to measure, right? Because force, if you think about it, is not really about your fingertip force, but the overall force you exert to the object. So it's a kind of force transmission problem that can you actually estimate how much overall force you exert on a given object, in addition to your fingertip sensing of tactile. So that's an incredibly hard problem that we will have to solve. But now we don't actually have the hardware to be able to measure force or tactile in a high enough of fidelity.
I have a question on top of that question. What do you think about event cameras to estimate force, tactile force?
Event camera. So event cameras are useful when you have a drastic change of speed on different things. But if you are talking about tactile and force, I think they're mostly invisible from egocentric view. So if you think about like when you're holding something, you're the contact, you don't directly like see the contact between the fingertip and the object because by definition it's occluded, right? So unless you put the event camera inside your fingertip like gel site, that might be something to look into. But again, I think we don't have the right hardware for measuring force or tactile yet. At least like if you want to bridge the human-robot gap. Yeah.
Hello, another question. Thanks for the talk. I imagine across these results, like every time you had a task, it was a model that was trained specifically for that task. And you showed some of that distribution alignment type stuff with, but I'm kind of just interested in your thoughts on like continual learning. So would this egocentric human data show like better performance in this like continual learning setting than kind of teleop? And what are your kind of predictions on that? Yeah.
That's an excellent question. I think this is more of like, so my view about continual learning is that human data is more suitable for studying this problem because you can imagine a setting where you want to adapt your home robots to a new home just by observing how humans like interact with their environment in their homes, than sort of having the human collect robot teleoperation data to adapt the robot to the new home. So I don't have a particular good idea about how to solve this problem from this sort of algorithm sense, but I think it's a very kind of suitable problem to be studied in a human to robot transfer setting. Yeah.
Cool. Thank you very much. Let's thank Danfei again for the amazing talk.
All right. Thank you guys.